the metal that refused to melt. Imagine a rocket engine during launch. Inside the engine, temperatures climb to nearly 1100 degrees, hot enough to weaken most metals. At those temperatures, ordinary alloys slowly deform under pressure, stretching like soft taffy until microscopic crackers appear. Now imagine you are trying to 3D print those engine parts. That's where the problem began. For years, aerospace engineers loved 3D printing because it could create shapes impossible with traditional manufacturing. Lighter fuel injectors, intricate cooling channels, complex turbine geometrics. But there was one huge limitation. The printed metals couldn't survive the heat. NASA needed something radically different, so instead of starting in a laboratory, NASA started inside a computer. At NASA Glenn Research Center, a scientist developed GRX 810, a new metal alloy specifically designed for additive manufacturing. What made this revolutionary was not just the alloy itself, it was the process. NASA used computational modeling to simulate thousands of material combinations before ever creating the physical alloy. That dramatically accelerated development. The final alloy combined nickel, cobalt, chromium, and nanoscale oxide particles. These tiny oxide particles are the secret. NASA engineers compared it to powdered sugar coating donut. The metal particles are the donuts and the oxide coating is the sugar. When the metal is exposed to extreme heat, those oxide particles stop the material from deforming. The result, GRX 810 can survive conditions that could crack traditional affordable alloy within hours and potentially last up to a year under stress at 1100 degrees. That's not an improvement, that's a category change. Commercial aviation burns billions of dollars in fuel every year because engines lose efficiency under extreme temperatures. A company called Vectoflow is testing GRX 810 flow sensors inside turbine engines. Normally, those sensors burns out rapidly, but if the sensors survive longer, engines can be optimized continuously. Fuel consumption drops, emissions decrease, maintenance costs fall dramatically, so a material designed for rocket engines could quietly make future airplanes greener and cheaper. High-temperature industrial system, gas turbines, hydrogen infrastructure, energy plants all suffer from thermal degradation. GRX 810 heat resistance opens possibility for cleaner energy systems, longer-lasting industrial turbines, more efficient heat exchangers, and lightweight power generation components. The hidden story here is that the better materials often create entire new industries. One of the most interesting parts is the commercial side. NASA didn't keep the technology locked inside government labs. The agency licensed it to Elementum 3D, a Colorado-based company that now produces GRX 810 commercially. That's the real NASA spin-off story. Space exploration doesn't only create spacecraft. Sometimes it creates a material that reshapes industries back on Earth. The technology teaching spacecraft how to land. Landing on the moon sounds simple until you realize something terrifying. A spacecraft descending toward the lunar surface has no GPS, no road signs, no atmosphere to slow it down, and sometimes only seconds to avoid disaster. A small navigation error can mean crashing into rocks, tipping into a crater, destroying $1 billion mission. NASA needed spacecraft to do something humans do naturally: understand motion in real time. So they taught a spacecraft to see. NASA developed Navigation Doppler Lidar, or NDL, at Langley Research Center. The system fires multiple laser beams toward the surface. When the light reflects back, the spacecraft analyzes timing, frequency shift, beam angle changes. This reveals exact altitude, direction of movements, speed relative to the ground. It works simply to police Doppler radar, except using light instead of radio arrays. In simple words, the spacecraft constantly asks the moon, "How fast am I moving toward you?" And the moon answers through reflected light. Traditional landing system estimates movements indirectly. NDL measures it directly. That matters enormously because lunar terrain is chaotic. Dust, slopes, boulders, craters, lighting extremes. The technology gives a spacecraft real-time awareness during descent. This was so effective that it became part of the first commercial lunar landing mission by Intuitive Missions in 2024. That's historic. This isn't a lab experiment anymore. It already helped commercial spacecraft land on the moon. The company Pezunic, founded by former NASA engineers, licensed the technology and improved it. Their upgraded version is smaller, lighter, and more power efficient. The same laser navigation principles are now useful for autonomous drones, robotic vehicles, industrial automation, precision mapping, and advanced aircraft navigation. Pezunic's newer system is also being integrated into Axiom Space commercial space station. And why? Because docking two spacecraft in orbit is essentially a controlled collision. The most powerful narrative angle is this: for decades, moon landings were something only governments could attempt. Now, private companies like Intuitive Machines, Robotics, Axiom Space are building on NASA technology to create a commercial lunar economy. And one laser navigation system is quietly becoming part of the future. Before humanity can live on the moon, spacecraft must first learn how to land safely. Navigation Doppler Lidar may become one of the invisible technologies that makes an entire lunar civilization possible. These two technologies work extremely well together because one represents surviving extreme heat and the other surviving extreme precision. Space exploration is no longer science fiction engineering. It's becoming industrial infrastructure.